Welcome to lecture number 22 for ECE 461 control systems, gain compensation using root locus. Now in the previous lectures we looked at root locus plots. With the root locus, the poles shift as I change the feedback gain, and I can see from the root locus plot how it's going to behave. For example, if I increase k, I can go from a pole which is on the real axis, start shifting left, speeding it up, then becomes complex. What we want to do is find the best value of k, meaning the largest possible gain that doesn't give you too much overshoot. High gains are good. As the gain increases, I get a quicker and quicker system. If it gets too quick, too much gain, I start getting overshoot. So that's typically the goal for gain compensation. Maximum gain that doesn't violate my requirements. To find k from the root locus plot, let's look at the following system. Again, from our root locus, any point on the root locus, g times k is -1. The angle condition gives you the root locus plot. For example, if I have poles at 0, -2, -5, these two poles come together, split apart, and become complex. The amplitude condition, the 1, tells you what k is. So any point on the root locus, g times k is -1. If I plug in, say s equals -0.1, this point, k is whatever it takes to make the gain 1. G has a gain of -21. The minus just says I'm on the root locus. The amplitude tells you k. K should be 1/21 or 0.04. What that gives you then is a type 1 system, no error per step input. The settling time is 4/0.1, 40 seconds. And if I plug in this number, 0.04655, into the closed loop system, like in VisSim, I can check. Is my design correct? So here's your plant, there's k, close the feedback loop, and sure enough, I've got about a 40-second settling time, no overshoot, tracking, it's a type 1 system, everything that I expected. Second example, again, the root locus plot is your shopping list. I can place the closed loop poles anywhere I want on the root locus plot. The question is, where do you want to put them? Suppose I want to put the closed loop poles at -0.5. In that case, again, any point on the root locus, g times k is -1, or 1 at 180 degrees. Solve, I get -5.9k. The minus sign tells me I'm on the root locus, angles add up. The amplitude tells me k. K is 1/5.9, k is 0.168. Again, I'll have no error per step input, it's type 1. I'll have no overshoot, it's a real pole. But now the settling time is 8 seconds. And throw that in VisSim, and sure enough, the settling time is about 8 seconds, no overshoot, real pole. Again, just what the root locus predicted. Third example, suppose I want to put the pole right here, -0.5 plus j 1.9. Again, any point on the root locus, g times k is -1. Plug in that point. This is another way to do this. This is in MATLAB. Evaluate g of s at s equals -0.5 plus j 1.95. And I get negative real. The complex part should be 0. If it's not 0, the point I picked isn't on the root locus. This one is, so that looks good. K is just 1 over that, 1.2. I'll take the real part. And it's a check. Find the closed loop system, gk over 1 plus gk, and one of the roots should be where I put it. If I look at VisSim to check my answer. Again, on the homeworks, this is a good way to check your answers. If you do a screen dump like this, it's easier for grading. I can see here's your system, here's the gain. I've got 20% overshoot, or whatever overshoot is. Yep, you did it right. Going back to VisSim, plug in 1.2, the gain that I calculated right here. And I've got a pole at -1, -0.5 plus j 1.93. You can see that the -0.5 says the settling time is 8 seconds. 1.93 says the frequency of oscillation is about 2 radians per second. So this is about pi. That's about 2 pi. The period is roughly pi. So frequency is 1 over pi radians per second times 2 pi gives you hertz. Something like that. But anyway, so that one checks out. So what that example did is it showed root locus actually works. If I draw the root locus and then pick up different spots on the root locus and calculate k and plug it in, that's the response I get. K, put the pole right here at minus 0.1, gave a real pole, no overshoot, 40-second settling time. Putting and close the pole at minus 0.5, made it an 8-second settling time. 0.5 plus J1.9 gave an overshoot, oscillations at 2 radians per second, 8-second settling time. The root locus is actually predicting the behavior of the closed loop system. So, suppose I want to find out what's the best value of gain. What's the best value of k? Well, what you want to do is I want the biggest gain possible. For example, as I move along the root locus, k increases. I want the biggest k possible because high gains give you better tracking, quicker response, less error, all the good things. But not so much gain that I have too much overshoot. So typically what you do, if my constraint is keep the overshoot less than 20%, what I do is I design right here. Design for 20% overshoot. So suppose my requirement is this. I want the biggest gain possible. Overshoot has to be less than 20% or equal to that. What's k? Well, from the second order approximations, 20% overshoot means the damping ratio is 0.4559. That tells me the angle of the pole. That tells me the point on the root locus. So what I do is on this root locus plot, I go up, turns out to be 63 degrees, go up at that angle until I hit the root locus plot. At that point, that's my design spot. Find S at any point in the root locus, d times k is minus 1. Evaluate g of S at this point. Pick k to make the gain 1 there. So, if I know the angle of the pole, I search along that line until the angle is out to 180. Turns out this is the point on the root locus that has a damping ratio of 0.4559. At that point, find k. And to do that, evaluate g of S at that point. That should be negative real. That's almost 0. Seeing this point isn't exactly in the root locus, but close. K is whatever it takes to make the gain minus 1. So in this case, k is whatever that, 0.6539. If I then take the closed loop system and simulate it, sure enough, I've got 20% overshoot. Second example. And let me show you kind of a quick way to do that in MATLAB. If I input my system, input your system G, and to draw the root locus, let's guess K. And what that really tells me is that I don't know what K should be. I'm going to guess it's somewhere between 10 to the minus 2 and 10 to the plus 2, 0.01 to 100. Take 1,000 points in there. And now draw the root locus plot. Draw the root locus of that G and K. And it's thinking. Got 1,000 points in the root locus, so it takes us some time. Okay, so there I've got the root locus. I want to find out what point has a damping ratio of 0.4559. And to do that, let's find the tangent. That's the angle, 1.09 radians. The tangent, what that tells me is rise over run. I'm going to hold that plot. That freezes it. Now plot, I'm going to go from the origin to minus 5 on the x-axis. From the origin to 5 times 1.9523. Let's make that in magenta. That drew the damping line. Again, the angle is 1.09 radians. Tangent tells me rise over run. That gives me the slope. I can now zoom in. Let's zoom in to this part of the graph. Zoom in some more. If I really want to get that point, zoom into here. There's my design point. It's minus 0.68 plus J1.34. Or showing off a little bit. 1.6811 plus J1.3623. Okay, so that's one example. Let's do a second example. Let's take the heat equation. The heat equation we looked at a little bit before. I've got a 10-stage RC filter. If I make the left point 1, this is the step response. Okay, trying that again. Here's the step response. The left endpoint is 1, and you can watch the temperature or voltage propagate down the right. So that's the open loop system. Let's apply feedback and try to force the tip to go to my set point, go to 1 as fast as I can, but don't have any overshoot or have 20% overshoot. So to do that, first thing I need to do is model the system. We did that before. Using state space, I get a 10th order system. Here's the transfer function. 10th order is kind of a pain to deal with, so let's just keep the dominant pole, and somewhat arbitrarily, let's keep the dominant 5 poles. So I'm going to keep the slowest pole and the poles that are 50 times faster or less. So here's my 5th order approximation. The numerator just matches the DC gain. Draw the root locus of this 5th order system. Do that, I get this. 10th order system has a couple other poles over here. They don't affect the root locus all that much. Now that I have the root locus, this is my shopping list. As I increase the gain K, I'll get a faster system. Then I start getting overshoot. Then I go unstable. Suppose I want to make the system as fast as possible with no overshoot. So my design point is right here, the breakaway point. That says S should be minus 1.05. To put the closed loop pole there, I calculate K so that G times K is minus 1. G of S at that point is minus 0.83. The minus sign says I'm on the root locus. Tells me that K is 1.2. Throw that in MATLAB, I can form the closed loop system and find out where the closed loop poles are. And sure enough, there's a pole at minus 1.05 because I put it there. I picked the gain to put the closed loop pole at minus 1.05. I can also check in MATLAB if I simulate this. Let's make V0 1.02, and I forgot the answer. Let's make the input 1.022, that's K, times the difference between the set point and the output. Run that, and it doesn't like me. Okay, running that, fixing the parentheses. Here's the step response. The step response in MATLAB showed node number 10, and notice node number 10 kind of paused, then it warms up. The input, the base temperature, is the difference between the set point, 1, and the tip temperature, times 1.202. If I make the gain 1.202, I get no overshoot. That's the quickest response I can get with no overshoot, and let's show that again. So give it a step input. It warms up, and then settles out without any overshoot. That's the power root locus. I got this response. I didn't have to iterate. This is nice because if your boss says, well, can you do better? Well, I can answer that. No, I can't. Because the root locus plot tells me that if I make the gain higher, I'll get overshoot. I'll violate one of my constraints. So this is the fastest I can get with no overshoot. No overshoot. And also notice on the left, where that 1.202 comes into play, the initial voltage. Stop. The initial voltage is 1.202 because ref is 1, the initial output is 0. So to go to 1, I actually make it 1.02. That's like when the light turns green, you floor the accelerator, then back off. That gets you a quicker response. So that was for no overshoot. Suppose I could tolerate 20% overshoot. In that case, what I do, I draw my damping line, same trick we did before. Here for 20% overshoot, the damping ratio is 1.4559, and it's basically almost 2-to-1 ratio. Go over 2, go over 1, up 2, over 1, up 2. So draw a line that's 2-to-1 ratio. And then see where that line intersects the root locus. Turns out that intersects at minus 0.7 plus J 1.36. To find k, any point on the root locus, g times k is minus 1. So find k to make the gain 1 there. So evaluate g of s at your point, and you get a number. It's not quite negative real. There's a complex part. It says that this point's not exactly on the root locus plot. It's close, but a little bit off. So take the magnitude, whenever that's k, 5.32. If I simulate that in MATLAB, k is 5.32, find the closed loop system and plot it, I'll have 20% overshoot. Okay, that's 20% above the DC level. If I go into the simulation, again, remind myself, k is 5.3217. So make that 5.3217. That's my gain compensator. Now what it should have is initially the voltage goes to 5.2 off the screen, then backs off. By applying more heat, it warms up faster. But I get overshoot. And I should have 20% overshoot. So if I try that, there's the input, went off the screen. That high input warms up the base, warms up the tip. Tip warms up, overshoots just a little, and then comes back down to steady state. There's your 20% overshoot. To do that, the input had to slam really high. Basically, heat equations don't like to oscillate. You can do it. If you apply enough thrust, enough input, I can make it oscillate. In fact, there's a saying at McDonnell Douglas, in thrust we trust. Put a big enough engine on it, anything will fly. Likewise here, have a big enough input, I can make the heat equation oscillate. It's going to take a really big input, but I can do it. Again, showing that again. There's my t equals 0, it runs, warms up the tip right here, gets a little bit of overshoot, and then comes back down. That's gain compensation. What root locus does is I can get the answer that I want in one shot. I don't have to iterate. The nice thing about that is sometimes I don't want to sit there and play with the gains, try to get it right. For example, used to work at GE aircraft engines. It costs $10,000 a minute to run an engine in a test cell. You don't want to be spending $10,000 every minute just playing with gains. You kind of want to know what the answer is before you start the test. In addition, if you get it wrong and you blow the engine, that's $4 million. So you kind of want to make sure you know what the gain is. You want to know what you're doing before you start a test. Root locus tells me before I did the simulation, this is the answer that I want. So likewise, I can sit there and test it and get the 20% overshoot very quickly using calculations. That's lecture number 22 for ECE 461 Control Systems, Gain Compensation with Root Locus.